Okay, so let's try and do a proof that Prim's algorithm will actually lead to a minimum spanning tree. So before we get to the proof, let's talk about some concepts that will be useful as we're going through the proof process. So we'll look at some concepts, assumptions, and properties. So first off, a tree can be thought of as an undirected acyclic graph. So that acyclic part is actually important. So we'll also be assuming non-negative weights. So when you're adding a new edge, you're either keeping the overall cost the same or making it worse. Some of the properties of a minimal spanning tree are that if you add any edge to the tree, it's going to cause a cycle. So if you remember, there are n-1 edges and n vertices. Adding any additional cycle, kind of by the pigeonhole principle, will basically end up connecting two vertices that were already part of the set of connected vertices. Going hand in hand with that, if a cycle exists, there is some edge that can be removed and still have a connected tree. Okay, so those two properties are about spanning trees in general, not about minimum spanning trees. So if you've got a spanning tree, adding a new edge creates a cycle in an undirected graph. And if you have a cycle in an undirected graph, there is some way to remove some edge and still recover your spanning tree if there's a single cycle. Okay, I also wanted to look at a slightly augmented version of Prim's algorithm. So this is the initialization that we've already seen with just one other minor thing. We're going to keep track of a set of edges. So T will start out as the empty set, and we'll gradually add edges to it. So T will actually represent the edges that compose our minimum spanning tree. So the second modification would be when we actually remove vertices from the priority queue, the vertex will be associated with some edge, the edge that we use to get to that particular vertex. So we will also go ahead and add that to our set T that represents our incoming edges. So for our starting node, it won't have an incoming edge, but all of the remaining vertices in our graph will. We'll also have to keep track of that edge. So every time we do our update of our distance estimates, we'll also update which edge is used to achieve that particular distance. So minor modifications. The really important part here is that we're going to be thinking of T as being the minimum spanning tree's edges, and we'll be slowly building that up over time. Okay, so let's go ahead and start constructing our proof of Prim's algorithm. So first off our assumptions, we've got a connected graph. So there is some path from every vertex. It's undirected, and our weights are greater than or equal to 0. So our question is the final T, the final set of edges, really optimal? Is it a minimum spanning tree? So our claim that we're going to try and prove is that every time we add a new edge, the current set that includes that new edge is a subset of some minimal spanning tree. Okay, so every time we're adding a new edge, we're always building towards some MS valid minimal spanning tree, MST. And then once all of the edges span G, it's got to be a minimal spanning tree. Each individual step got closer and closer to a minimal spanning tree. So once we have enough edges, we'll have a minimal spanning tree. Okay, so again, that's our overall claim. So you can kind of think of our progress as continually adding edge after edge. So we'll do a proof by induction where basically we'll be thinking about this process of continually adding edges. So we're going to be doing induction on kind of the number of edges. So our induction hypothesis is that the edges that we currently have already form a spanning tree, and we're going to think about what happens as we add an additional edge. So just like always with a proof by induction, we also have to have a base case before we get too far. We'll go ahead and establish that. So our base case will be at the end of our initialization of our algorithm, we have 0 edges added. And we can think of our induction step as being adding the next edge. So as we're going through this proof, I'll use the notation T star to indicate some minimal spanning tree. So it's some sort of a valid solution. Okay, so got our claim. let's focus on our base case. So our base case is when we have 0 edges. So our set T is empty. And the empty set is a subset of every set. So it's definitely a subset of some ideal solution T star. Okay. So at the beginning, our base case is guaranteed to be true. Okay, so again, we're going to think about what happens as we add edges. So let's think about kind of 2 groups of edges. So we've got this connected set of edges. So the things that are already in T are the things that are already removed from our priority queue, however you want to think about that. And then we've got this other set, this set of stuff that's not yet connected, or it's still in the priority queue. So each time we add a new edge, we're adding an edge to something that is not already connected. So if you remember, the criteria in our if statement is that it has to be an edge to something that's not already marked as connected. So it's going to connect between these 2 sets. Okay. Okay. T is already going to be some subset of a minimal spanning tree, T star, prior to adding that edge. Okay. Now let's also consider a secondary edge. So the secondary edge, which we'll refer to as E prime, also connects these 2 sets of vertices, the ones that are still in the priority queue versus the ones that have been removed. So the ones that have been removed are the ones that are in T. So we'll consider both at the edge that we actually remove for Prim's algorithm and this other edge, E prime. And E prime will be something that connects these 2 set of vertices in a minimal spanning tree T star. Okay, so prior to thinking about adding this new edge E, we know that everything in T is also in T star. Now we're going to be thinking about this new edge that E that will connect T to T star. This new edge E will be chosen by Prim's algorithm. We'll also think about another edge, E prime, that's still between these 2 sets, but it's some edge in T star, the minimal spanning tree that we're probably building towards. Okay, so 2 edges, E and E star. And again, E we're going to add to T, and it is the edge chosen by Prim's algorithm, and E prime is something in T star that also connects together these 2 set of vertices. Okay, so option 1, they're the same. This thing that we picked as E using Prim's algorithm is E prime. It's the same thing that would be in that would be one of the edges of the minimal spanning tree. So when we add it, we're continually getting closer to T star. So adding E to T will still be a subset of T star. Okay, so that's great. This actually is what our goal is. We want to demonstrate that each step, adding each individual edge, brings us closer to a minimal spanning tree. And this is kind of a trivial case where if we pick an edge that is part of the minimal spanning tree, our ideal T star, then we're closer to that goal. Okay, let's talk about the other case. So option number 2 is when E is not E prime. Okay, so let's consider what happens if we were actually to add our new edge E, the one that we're picking with Prim's algorithm, to T star, our minimal spanning tree. So if you remember, T star is already a tree, so it's already a spanning tree. Adding any edge to the spanning tree will create a cycle. Okay. Okay, so this particular combination definitely has a loop in it. And the loop will be kind of between those 2 clouds of nodes. So since there's a loop, so we've got kind of our nodes that are in the priority queue and our nodes that have been removed from the priority queue and our nodes that are in the priority queue. So we've got this E that's going to connect them, and we've got this other E prime that also connects them. And if they're not the same, we've somehow got a loop between these 2 groups of things. So if we add E to T star, it creates this loop. But we can break this loop by removing some edge E prime that was in T star. So if we kind of remove this edge, or remove some candidate edge between these two, we can break the cycle. Okay, so the basic idea here is we'll create a new spanning tree, not necessarily a minimum spanning tree, but a new spanning tree by taking our ideal solution, adding in the candidate edge that Prim's algorithm selected, and removing whatever some duplicate edge that was in this original T star. Okay. So the idea is by adding our edge E, we create a cycle. By removing some other edge E prime from T star, we'll break the cycle and be back to a spanning tree. Now the question is, if we have that spanning tree with the broken cycle, is it minimal? Okay, so Prim's algorithm picked E rather than E prime, so we know that the weight of E had to be less than the weight of E prime. Okay, so if we think about the overall sum of weights, or capital W function, the weight of this new tree, T prime, basically all we've done is we've substituted one edge for another edge. It has to be the weight of our minimal spanning tree, T star, minus the weight of the edge we removed, plus the weight of the edge that we added. Okay, and we know that the thing that we added was at least as good, if not better, than the thing we removed. So overall, we could have only improved this. Okay, again, and this is partly because we're assuming non-negative edge weights. Okay, so the overall idea here is that T prime has to be at least as good as T star. And T star was a minimal spanning tree. By definition, it's already as good as it can get. So T prime must also be a minimal spanning tree that contains T union with this additional edge E. It might be a different set of edges that forms a minimal spanning tree, but it also has to be a minimal spanning tree. So we've exchanged this edge, and it still leads us one step closer to some minimal spanning tree. So each time we add an edge, the edge is getting us closer to some minimal spanning tree.